But it was running through a program, you follow me? And so there'd be a slight delay. We'd hit enter and be like, and then my screen would pop up with the answer. Or maybe his would beat mine. Now with these, it's just what? It's instant. It's like, boom.
Oh, that's Casio.
Technology, right. But yeah, it'd be like a Casio EP500 versus the Radio Shack version, etc. But it's kind of neat, but that's what we're talking about now. We get these error bounds to limit the amount of times or the number of iterations. So let's do one with trapezoidal rule. This T stands for trapezoidal, that M stands for midpoint rule. This N stands for Simpson's rule. Do you notice we have to do second derivatives in something like this? May look weird there. Don't let this be intimidated whatsoever. I thought we'd start with the integral from 1 to 2 of natural log of x. Now we know how to get that exactly, don't we? Anyone know how to get that?
1 over x.
Or does anyone know how to evaluate that definite integral exactly? Well, wait. I like yours better. Because that would require integration by parts, wouldn't it? I heard you say 1 over x. I prefer that integral. The last one would have needed the integration by parts. Do you agree? Natural log of x. Let's use 1 over x. All right. So we're going to do 1 over x dx. We're not going to get it exactly. What's the integral of 1 over x? Natural log of x. You plug in a 2 and a 1, you get natural log of 2 minus natural log of 1. What I want you to use, and how do they word this in the book? How large do we have to choose them? That's what they ask. How large do we have to choose n? We're going to estimate this with a trapezoidal rule. Well, how large do we have to choose n so that trapezoidal rule approximation are accurate, in this case is, to within 0.001. Oh. How large do we have to choose n? And this number of subdivisions. So the trapezoidal rule approximation to that integral is accurate to within 0.001. Someone can use 0.0001. .0001. That will give it a few more subdivisions. Okay, so a question like this, and I hope this gets your curiosity going, because now we're saying, boy, we can figure out using the trapezoidal rule how many of these subdivisions, n, the n value, we need so we can be that accurate so we can actually store this into a computer. Tell when it's, use this amount of subdivisions, rather than just using n equal to 1,000 every time, which could be time consuming, true? On a computer. So if we're using trapezoidal rule, everyone, here's the error bounds formula. It's k times b minus a cubed over 12n squared. Alright? Now, this k value is some constant such that the second derivative and its absolute value of the second derivative of that function right there is always less than or equal to k. So the first thing we have to do, here's the function, f of x equals 1 over x. We gotta find the first derivative and then we gotta find the second derivative, don't we? That's our first step. But we're gonna use the error bounds formula to calculate this. But that k value comes from the absolute value of the second derivative of f of x. So we're gonna start there. F of x equals 1 over x, which is x to the what? -1? What's the derivative of x to a -1?
-1
-1 x to -2. I like it. What's the second derivative? Two x to the -3. And what's another way to write that? 2 over x cubed. Okay, we got it. Now we gotta decide what to use for k. So when we got the second derivative, right? So don't let this intimidate you at all. This is kind of fun. Because we're just gonna plug it into the formula. We're gonna solve for this letter f. But we did have to start with getting this k value. Now we know what the second derivative is, right? So we're looking for this k value such that 2 over x cubed is always less than or equal to k. Always, no matter what, on the interval from 1 to 2. Now you might say, well, why don't you just use 1,000? And when the absolute value of this is always less than 1,000, remember what we're saying, we're like, get that number, the best number we can use. So what were the limits from a to b? Say go from the a value to the b value. So let's plug them in. And if you plug 1 in there, what do you get? What's 2 over 1 cubed? 2. I'm going to write that down. That's if I plug a 1 in there. Plug the other number in there. Oh, and what is the absolute value? In case it came out negative, you make it positive, right? Now when I got this by plugging in what? I plug in the endpoint a equals 1. Would you now plug the value b into that? What do you get? 2 over 2 cubed? What's the absolute value of 1 2/8 or 1 what? 4? All right, which number is bigger? That's the number we got to use.
2.
We're going to use k equals 2. And I'll stop to make sure everyone knows why we're using k equals 2. Why am I not using a smaller number? I plugged in one endpoint, 1. Second derivative is 2. I plugged in the other endpoint, 2. And I got a what? 1/4? We've got to come up with a k value, so this is what? Here's the word. This is always, no matter what, over that interval, the second derivative is always going to be less than or equal to a what? 2. Does that make sense? I could have used 1,000, but we're like, my goodness. Use the smallest number you can that's possible, but I couldn't use the 1/4. Because do you agree, everyone, the second derivative over that interval is not always less than a 1/4? Cool. Does anyone know why reason 2?
Trying to maintain that condition to be true.
That's right. Make that condition to be true, it's always got to be true. That's why I put the word always. Because it always has to hold over the entire interval. So I'm going to use k equals 2. And I know you're going, can't you use k equal to 10? Yeah. I mean, 10 holds true, but this is the best number, right? This is the best number in terms of we want the lowest that we can use. So it always holds true. All right, now, let's write this out. What do we have here? This error, which is what? K times b minus a cubed over 12n squared. And we want to know when it's always less than how much? 0.0001. This is all we're going to do, everyone. This is not going to be hard to solve. What's the k value we're using? 2. Let's start plugging in the numbers. 2. What was b minus a? 2 minus 1 cubed. 12 n squared less than 0.0001. We're just going to solve this. Hey, students always ask me when I present this, why did you put an equal sign? And the reason is because they said the wording within. I want to point that out. That's why I'm not putting an equal sign here.
Within is not inclusive?
Exactly. Within is not inclusive by that wording within, so we'll just put a less than. Great question. So you'll notice when we get our answer, we're just going to round up the integer.
And the text will be the wording for something that's inclusive.
Yeah. And the wording would be similar to this. Hey, what are you getting? How do you solve this? I get 2 over 12n squared less than 0.0001. How do you solve that? Can I multiply n squared on both sides? Can I divide that 0.0001 on both sides? But how do I get in? Take the what? Square root of that number, right? So would you take the square root of that number? We'll find out what n has to be greater than. Let's get this accuracy. Okay, how I algebraically manipulated that? Okay.
Why is the less than sign going towards the 0.0001 within the arrow?
Oh, great question. We want this, we're thinking this is the error bound, right? And we're thinking it has to be, we want it as small as possible, but within this. So that's why I'm using less than this.
So then, what is
You can
the-
almost, if you want, ignore that part.
Oh, okay.
I know, it can be a little confusing, but you're like, the whole idea is, hey, this is my error bound, I wanna know what this has to be within the error that they state. Great question. The only reason I didn't put an equal is because they said within. So in the end, I can just go n is greater than some number. Hey, what do y'all get?
40.824.
Now, how should I answer this question? So Armando, I want to make this an integer, but I want to use the next closest integer I can. Keep in mind, trapezoidal rule can be odd. The only one that has to be even, which was rule? Simpson's. So trapezoidal rule can be odd. What will I use?
41.
41? This is the answer to the problem. Use n equal to 41. You could check this too. Use n equal to 41. You'll have accuracy within that right there. That's how accurate it is, within a 0.0001. So if this is stored into a computer, the computer can run and say, hey, make sure to run 41 iterations to get that accuracy. Or if they want 6 decimal places, okay, 0.000001, right? That's an easy thing to calculate if you want to go look at that.
So we need to memorize these error bounds for the test, right?
You know, good question. I usually get the error balance. If you, yeah, I know there's so many other things I'm having. Memorize this, Connor. I want you to know, like all those trig identities. I get the error balance. That's just me.
Okay.
You know, and if there's like, if I find that we're covering what, I give a test, and it covers all this stuff from what trig substitution to what else do we do? The trig integrals. We'll be doing improper integrals tomorrow. If there's not enough time, we'll definitely have you use these approximation methods, but if there's not enough time, I don't think there's gonna be enough time in class to include this, and I'll give you a heads up about that as well. And you can ask me that. So, hey, I know we're doing this in the work, but are you still gonna be able to include the error bounds on the test? But when I want to be clear about that, I would provide that for you. Even though, yeah, I can memorize this and all that, it's like, give them the error bounds and let them compute it, right?
So for these kinds of problems, n will never be an inequality. We always
That's
have
right.
n as a
Always go up to the next integer. And then, Armando, if it's Simpsons, make sure to make it even. So in this case, let's say we're running Simpsons rule here, Armando, 40.8, I would have made this 42, because it has to be even. Awesome. Hey,
So you would never round down?
that's right, you always round up. You always round up. You will always round this up. That gives the within. Because think about it. I could have used 1,000 here. I'd get better accuracy, right? Using an infinite amount, you're going to get the best, right? But like, hey, this thing can't run forever in an infinite loop. And running 1,000 is like that computer I had where it just like, has anyone ever noticed slight delays on these? That's when something's really running through something that took a while. You're like, whoa, it took a while for that to pop right. You know, it might be like a second and a half. Hey, great job with this. I thought the last one we'll do, we did an error bound for trapezoidal. Let's do an error bound for Simpsons. But I wanted to give you, this problem wasn't so cool, you know why? Don't we know the exact answer? So you are sitting there going, this isn't so meaningful for us. So let me throw something up here that we haven't seen before. We're like, G-sub doesn't work. This is one of my favorites, look. EDX squared. And we're going to use Simpsons rule. Hey, if you're curious, if you want to look at Simpsons rule on that last problem, you totally could. Just notice Simpsons rule, everyone, it's not second derivative anymore. It's not second derivative anymore. Look what we got to do for the supposed part. That's the fourth derivative. So we're going to have to go up 2 more notches for that interval we have to do, right? But if you wanted to compare it to the last one, it's pretty interesting. Simpsons rule uses way less number of subdivisions. It's pretty cool. It's a great method. That's why a lot of CAS, when I say CAS, CAS, computer algebra systems, will use Simpson's rule. Pretty efficient, isn't it? Using those parabolas. It's really neat. And you take a numerical analysis class, you'll see this stuff again. Pretty neat stuff. But Simpson's rule would not take 41. Probably be closer to like, you can try it. Be closer, lower, like might be less than 10. Maybe less than 10. Well, that's what we're going to do. We're going to use Simpson's rule now. For e to the x squared. And we're going to be accurate. I want to, not 0, 0, 1. How about 0.00001? Hate to save time. When I knew you know how to do derivatives. This isn't a Calc 1 class, but you know how to do derivatives. To save time, can we talk about that fourth derivative? That is a fourth derivative, right? All right, can you just tell me, can you explain to me how to get the first derivative? What is it? Chain rule. 2x times what? But could you just tell me, this is just to save time, I knew you know how to do derivatives. What rule would you have to do if you wanted to do all the math to get to that fourth derivative? You would have to use what rule? Product rule. So can we just talk about that? You'd have to do what? First times the derivative of the second plus the second times the derivative of the first. Okay, you do that. But then you get to the third derivative, isn't that get more what? Complicated? Yes. And then the fourth derivative, you're like, okay, so what I'm going to do is just show you what is the fourth derivative. To save time. And you might think, isn't that cheating? No, this is the whole point. If you're curious, read problem number 23 out of the textbook. They discuss this. There's a long paragraph. They say, the beauty of the technology nowadays is we do have computer algebra systems. So even a problem like this, if you're trying to investigate it, you can use the computer algebra system to find that fourth derivative. Save you a little time, right? And then you can apply this formula. That's the whole idea. Cool, and you can actually graph the curve. If you want to look, let me look at the curve to see what because the hardest part, everyone, of course, to this formula is awesome. The hardest part is finding that k value. Do you all agree? Mathematicians agree. That's the challenge. Is what's that k value? Because I gave you 1 over x before. The second derivative of some functions sometimes are not so easy. And so you can use a computer algebra system to explore the second derivative and explore the graph to see what that k value is. Well, in this case, I'm just going to give you the fourth derivative. Hold up. I wrote this down. Ready? It is 12 plus 48 x squared plus 16x to the fourth, close the parentheses, times e to the x squared. That is the second derivative. But again, you could use a CAS to get this. Do you agree? You would do the same thing. You're like, hey, I'm exploring this back in my room, back in my home. I'm going to use a computer algebra system for this. Wolfram Alpha could do this for you too, true? But you might have a TI-89 or a TI-Inspire. We could find this. So there's the fourth derivative. Now, help me find k values. What's these endpoints? We got 0 and a 1. So, we got to find this. So that the fourth derivative of the function e to the x squared is always less than or equal to some k value. What the heck is k? So let's start. Let's plug a 0 in here. What would we get? So if I plug 0 into that fourth derivative, what's the fourth derivative at 0? E to 0 is 1. Is it just 12? All right. Plug in 1.
286.49 or 59.
Well, write it in terms of e. Could you do that? If you don't mind there, Andrew, can you tell me what it would be in terms of e? If I plug a 1 in there, 16 plus, what's 12 plus 48? 60? 76, and then e to what power? Andrew, do you get that? Tell me if I plug in a 1 and all that, you get that? 76e? Hey, cool. Which one are we going to have to use? Because remember, it has to be always less than k. Which one I use? Yeah, we're going to use this. And so you ready to do it? Crank it out. Now this is the one we want. K times b minus a to the 5th power all over 180 times n to the 4th must be less than the value 0.00001. And then what are we going to use for k? Okay, no. This is your k. That's the challenge though. And when you look at something more complicated, is how am I going to find that k? Well, use a computer algebra system and explore the 4th derivative of that equation to see what the k value is. Because this stuff is useful so that you get that desired accuracy that you want. So what I love about this problem, U sub doesn't work. Substitution rule does not work. Integration by parts does not work. Partial fractions doesn't work. Heck, trig substitution doesn't work. But now we know if we run a certain amount of iterations by Simpson's rule, we can estimate that to be accurate within this. All right, the k value is the what? The 76. Now, hey, before I keep going, does everyone know why I use 76e? When I looked at the endpoints of 0 and 1, I plugged in 0, I got a 12. I plugged in 1 into the 4th derivative, and I got a 76e, and I was like, which one's bigger? Because it always has to be less than that value, so we're going to use the constant k value, 76e. B minus a? Well, go ahead, Kate.
So because 76e is smaller than 12, that's...
Wait. Bigger than 12, I'm using the bigger value. The whole reason is, what we're saying here, I'm going to put this word always. This always has to be less than that value. See, the second derivative of that function, the 4th derivative of that function isn't always less than or equal to 12. You can tell. We got up to what? 76e. So we got to use the 76e, so we say that we know for sure that this always holds true over the entire interval, the k value.
So then we would pick the bigger number.
There you go. You can pick the bigger value. But I want to point out, Kate, it's like, is this so easy sometimes when these functions get more, I mean, for a mathematician, sometimes this thing can be really, really complicated, and the 4th derivative can be what? Really, so that's why we use, technology to assist us in this, like a computer algebra system. Hey, cool. All right. And to the 4th. Now, how do you solve this? What would n to the 4th have to be greater than? 76e divided by 180 times 0.0001. Zero, 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 4 zeros and a 1, and then n will take the 4th root of that number, right? How do you do 4th root on a calculator? Yeah, you could do caret to the 1/4 power. Will that work? So take this number right here and raise it to the 1/4 power. Caret 1/4. Or if I'm looking at your math menu, isn't there a root button? You can use number 5. Very good. But if you just want to do it off the front screen of your calculator, 1, 2, 3, 4, and a 1. Make sure n's greater than this. Oh, and Armando and everyone, I'm going to make this even. So whatever comes up, I'm going to make this answer even. I love this problem because we can't do that. By our integration methods, like how many would you actually run? If I wanted to use Microsoft Excel to get this answer, now this would give me an idea, because I don't know the answer to that. That's what I love about this. That's what I love about this topic here. I do not know that answer, because I don't know an integration method to it. But at least if I was using Microsoft Excel, I would say, well, I got to use at least this many iterations to get this desired accuracy. Hey, what do y'all get? Chad did it earlier, so let's see if I can see it over here. Anybody get a number?
20.
Okay, what'd you get before the 20?
18.
He got 18.4 for this number. He doesn't use 19 because it's Simpson's. It must be even, so he uses n equal to 1. So what I would do, if I was using Microsoft Excel, open up my spreadsheet, run 20 iterations, in terms of use 20 subdivisions, use n equal to 20. And my math formula here And I'll have this baby accurate to within this right here. Ooh, hey, great job. Hey, tomorrow we'll be doing section 7.8. Have a great day, everyone.